All right, last time we talked about NPDAs. We talked about what they were. We talked about some notation for how to refer to them, how to construct them. And I left you with the question of constructing an NPDA for the language of all strings that have the same number of A's as number of B's. And the question was trying to solve it with a stack algorithmically, because that I thought would lead people to the answer a bit better. So how did that go? Do we think we have a solution? All right, one person thinks they are close. Out of one people, we have one person here. So one person of one person thinks they are close. Excellent. So what we need to do here is we need to have two different stack symbols. We need a stack symbol representing that we've seen more A's than B's so far, and another stack symbol that says that we've seen more B's than A's so far. And again, I like using different alphabets for the string and for the stack. This does not have to be the case, but it certainly helps us as we are learning this and trying to differentiate between those two different alphabets. So the rules we're going to follow. If we read an A, we can't do anything for sure yet, because what we want to do will be different depending on if we've seen more A's than B's or if we've seen more B's than A's. Because the end result of this is that we need to store the number of more A's than B's that we've seen, or the number of more B's than A's. So if you see an A, if you've seen more A's than B's, we need to add 1 to the more A's than B's that we've seen. And if we've seen more B's than A's, then we want to subtract 1 of the more B's than A's that we've seen when we see the current A. So transitioning from this logic into the rules that represent that logic, we're going to say if the top character of the stack is a 0, then push another 0. If we've seen more A's than B's, add an additional more A than B that we've seen. That's what the 0 represents. The number of zeros on the stack is the number of more A's than B's we have seen so far in the string. If the top stack symbol is a 1, instead of pushing a 0, we can only have either zeros or ones on the stack in this case. We're going to pop a 1 rather than trying to push something, which says that we're subtracting 1 more B than A that we've seen so far. And now if we read a B, luckily we had one person online. It's not totally just me lecturing to an empty classroom, but it must be Friday or something.
Yeah.
If we read a B, we're going to look at the top stack symbol. And now you can imagine that if it's a 0, that means we'd seen more A's than B's so far. We're going to pop a 0, saying that after we read this B, we've seen 1 fewer A's than B's. And if we've seen more B's than A's, then when we see another B, that's going to add 1 to the more B's than A's that we've seen so far. The only way that at the end of the string, we have seen an equal number of A's and B's is if the stack only has the bottom of stack symbol on it. So maybe we pushed a Z at the very beginning of this as the bottom of stack character. And if we look at and see a Z on the stack now, at the end of the string, we know we saw an equal number of A's and B's. If there's a 0 on top of the stack, we know that there were more A's than B's in the string. If there's a 1 on top of the stack, we know that there were more B's than A's in the string. So what does this look like as an NPDA? I think I said there were 3 states in this last time. I think we might actually be able to do it with 2. If we assume no bottom of stack character, because usually you end up doing something with the bottom of stack character, either before you enter the first state or as something about you go from the first state to the second state, adding that bottom of stack character. But either way you do, it's gonna be right. How much juice we got? Just enough, probably. So we're going to have an initial state that we're going to call Q0, it's final. Because if you start, you've seen the same number of A's and B's. Does this make sense? This would have been right in the NFA world. But we're actually going to erase this and say this is not a final state. Because this is an NPDA, we're going to have a transition from this initial state to a final state, reading no characters in the input, which means that we can teleport to a final state, but only if the bottom of stack character is on the stack. So as we enter this, we're going to assume that we're kind of pushing a Z on the stack. So this can also have a transition associated with it. So what was in the past? I can go back to this so that we can see exactly what an NPDA looks like. That's what I want. We see the transitions tell us 3 pieces of information: the input character, what we pop from the stack, and what we push to the stack. So we want to, as we come into this, we want to read nothing from the input. We want to pop nothing from the stack because there is nothing on the stack, and we want to push the bottom of stack character. So this is how you can avoid having this is kind of a preliminary work before we enter the state machine. An initial state for this. Talked about instantaneous descriptions. Just want to make sure I don't overwrite anything. All right, so now we need some transitions within Q0 that are going to define what are all of the legal things that we can do from this state. And note that this is independent of the condition of where we are in the string. This tells us that there's no if statement ahead of this logic. This logic is always the same no matter where we are in the string. And that tells us that we don't need to be transitioning states. We can do all of this logic directly from Q0. So in Q0, if the top of stack character is a 0, then we want to push another 0 when we read an A. So this would be a loop back to Q0. It's going to read an A. It's going to pop the 0 to say the 0 has to be what's on top of the stack. And then what we want to push is the 0 that we popped and another 0 that represents the 0 that we read. And when we do this, we end up right back in that same situation. Let's write another transition. Let's say when we read an A, if we pop a 1, if there's a 1 on top of the stack, then we want to pop it, which means that we want to replace it with nothing. If we do that, then that's the equivalent of popping the 1 that was on top of the stack. We're pushing nothing in its place. If it's a 0 and we read a B, pop a 0. This can be represented with another transition back to Q0 that says, how do we want to do this? We read a B. If the top of stack character is a 0, then we want to pop it. Fourth rule says if we read a B and there's a 1 on top of the stack, then we want to push another 1. So we'll pop the 1 and we'll push 2 1s, which is the equivalent of pushing a single 1. So you can see that we're going to just be cycling in some path, Q0 to Q0 to Q0 to Q0 to Q0 to Q0 to Q0. And all we care about in that is we're manipulating the stack based on the input character that we read. Finally, we're going to be able to make a transition from Q0 to a final state, Q1. What does that transition look like? When can we make that transition?
On lambda when the bottom is Z.
Yeah, so actually we're missing two more transitions here of what happens when the bottom of stack character is that Z. So we see an A. If the bottom of stack character is the Z, then we're going to push the 0 that represents the A and the Z back on the stack. And if we see a B and the bottom of stack character is Z, top character on the stack is the bottom of stack character. There we go. We want the 1 representing the B and the bottom of stack character back. Finally, we want to be able to make that transition. So we want to be able to do this only if the bottom of stack character is that. So we can make a transition that does not read a single input character. We can teleport to Q1, but we have to be able to pop the bottom of stack character. And in this case, we actually don't want to put it back. So there are two different ways that we can do this technically. We're only supposed to be able to accept if we have an empty stack, which means that the bottom of stack character is gone. But in some cases, I have seen literature that says this is empty if what's on top is the bottom of stack character. So you would be right, and I will know what you mean if this last thing here is either a lambda or a Z. Both of these are going to be good enough for the scope of this class, but they're the only right answers. You'll want to be consistent with this notation for yourself. If this is lambda, then this accepting state says that the stack is empty when we get there, including that bottom of stack character. And we can only accept when the stack is empty, not when the stack has that bottom of stack character on it. If you push that bottom of stack character on, that means that you accept if and only if you're in this state and the top of stack character is the bottom of stack character. Either one of those are notationally correct as long as you state.
You said we would need over 3 states for this.
I did. You only need 2.
Okay.
The third state was coming from my idea of this was going to be a state and you make a transition from this state to this state, adding the bottom of stack character.
Oh.
So I'm giving you 2 options as well. You can make this a state and make this a transition from that state that adds the bottom of stack character. Or if you prefer a notation, you can have the arrow that points to the initial state, do some initial work that always happens, which is add the bottom of stack character.
And I'd like test it out, like you don't care which we do as long as we do number one of them.
Yep. Yeah. If you just have an arrow like this without this and adding a bottom of stack character, it will be wrong. You need to put that bottom of stack character on there somehow, either starting from a state where there's no initial work and doing that, or saying that this is always the initial work that happens before we enter that state. Again, you have some options. Just be sure that you know what you're doing and can describe it. I recognize that I didn't get yesterday's lecture video up yesterday, so Nathan's probably thinking, what the heck is going on? I can give you a very brief rundown after class if you'd like, or I can upload the lecture video and hopefully that is more useful than sitting here going, what the heck is this? Well, maybe you've seen it before. Maybe, no, we'll see. All right, questions on a solution to this problem? You can see how NPDAs are a little bit harder to read than DFAs and NFAs in some cases like this, where there are very few states. and tons of transitions within that same state. Because now we have transitions from a state to itself when we're manipulating the stack characters, which can lead to ridiculously dense graphs. So a lot of the time, it is actually easier to list the rules or the logic behind it rather than trying to draw it out, because this is just kind of a visual mess. Yes, it's visual, but I don't know if the fact that it's visual really helps very much. I'll let you make that call for yourself about what is more intuitive there. But I thought I'd try to give you as many different ways. So we went over how to write it out as a sequence of transitions. I've written it out logically on the slide here, and I've drawn an image on the board. Those are kind of your 3 different ways of tackling these kinds of problems from the start. So find something that is intuitive to you. We're going to get another example here after I think there's another image of exactly what I just drew, but I don't think it's quite correct. Let's look at the instantaneous transitions as well, or descriptions, sorry, instantaneous descriptions. Let's say we wanted to process BAAB. So here's the image that I just drew without the adding the bottom of stack character somewhere. So that's why I don't like it, is there's no state that adds it, and there's nothing on this arrow that actually adds the bottom of stack character. So that's why I don't like it. But other than that, there it is. So go ahead and write in instantaneous description form how this is going to try to parse the string BAAB. And if you need a refresher on instantaneous description form, there it is. So there's this notation. We have a tuple of 3 elements, a triple. You need the state of the control unit, the unread portion of the string, and the stack contents. And then you're going to do that turnstile. Then after a single transition, the next one, turnstile, the next transition, turnstile, the next transition, that shows based on how this triple evolves. Just continue to report these 3 elements for that NPDA for the string BAAB. So if you don't have this in your notes, go ahead and quickly write down what Q, W, and U stand for, as well as the concept of this turnstile symbol. I'll do the first couple. So we start in state Q0. The unread portion of the string is BAAB. And the stack contains just the bottom of stack character Z. After the first transition, now we're not keeping track of what we've read. All we care about is we're in the state Q0. The remaining portion of the string after we read the first B is AAB, because we successfully read the first B. What happens when you read that B? We add a 1 to the stack. That's this rule right here. So we apply this rule to this instantaneous description, and we get this instantaneous description. So what happens next? What happens when we read this A? Go ahead and finish this off. Hopefully we got something like that. So we're gonna read the A. When the top of stacked character is a 1, we're in the A1 case. So we're gonna replace the 1 on the stack with a lambda. So we successfully read the A. What's left in the string is just the everything after that A. And we have popped a 1 from the stack according to that rule. So we get rid of the 1 that's on the top of the stack, leaving us just with the bottom of the stack character. We're still in state Q0. Transitioning, we read the A when we have the bottom of stack character. So A with the bottom of stack character says push a 0. So we're going to remove the A from the string, still in state Q0 because it loops back to itself. We're gonna push a 0 to the stack. Next, we're gonna read the B. From state Q0, we go to state Q0. A B when there's a 0 on top says pop the 0, replace it with nothing. We're gonna pop the 0, we're gonna replace it with nothing. The entire stack is just the bottom of the stack symbol. What happens when we're at the end of the string? Is there anything we can do without reading any characters? Yes, we can transition to the final state when we have the bottom of stack character. Note that we could have also done that here. At that position, it was possible for us to make this transition. Does it matter that we didn't do that or didn't consider it? In this case, it doesn't, but in general, we want to. We have a branch here where we could kind of push a 0 onto the stack, but we also want to consider what happens when we make this transition. Note that there's nothing that we can do from QF to QF, reading any input, and because there was input left in the string, that would have led to failure. Because what happens when we start in QF and read an A from the string? We cannot accept unless there's nothing left to be read in the string. So even though we're teleporting to a final state, as soon as we try to read an A in that final state, we immediately reject because there is no such out edge from the final state. So we should have considered that here. We also should have considered that here. Whenever they had the bottom of stack character, this just says we can teleport. As long as the bottom of stack character is there, we do nothing to the stack, but then we have to be at the end of the string because there's no defined out edge for the string. So we need to know that we end in that accepting state with an empty stack. This does say we pushed this back. So if we really want it to be an empty stack, we would have to define an empty stack to be the only contents is the bottom of stack character, or we have to pop the bottom of stack character when we make that transition. The book defines it to be the bottom of stack character is the only thing on the stack. That doesn't count as something that we can remove from the stack. It just tells us that the stack is empty. All right, let's start back at the beginning. We're going to construct an NPDA to represent another language that we proved is not regular. WWR, that's a language that we remember. However, there is one stipulation to this. What does this stipulation mean? We remember what this positive closure is.
Means no empty string, right?
Yeah, it means that there's at least one of these. So this is the entirety of WWR that does not accept the empty string. Cannot accept the empty string because then there would be 0 of these. So this rule states that we want there to be a string of at least length 1 such that that string is itself followed by that in reverse. So let's give you I think we already said the empty string is not. What about the string A? Is that in WWR? No, it is not. It is a palindrome, but it is not half the string and then that same half in reverse. So this has to be an even length string. It cannot be odd length. And we have to, at the midpoint of that even length string, transition from reading characters forwards to reading characters backwards. The fun part is, how do we know where the middle of the string is? As we're reading this character by character from the left, how do we know where that is? You could have a fun situation like this. Where even the first half of the string is itself a WWR. So how would you accept this whole string when even the first half could be considered to be the endpoint of a WWR? I would argue that this question isn't anywhere near as hard or requires as much thought as you're going to put into this. Because this is an NPDA, it's non-deterministic. If there exists a path to a final state at the end of this, then we accept. So my hint to you is, don't even worry about that case. It's not relevant to the solution. So go ahead and give it a shot. How many states? What does the stack represent? What are the transitions between those states? Remember that with pushdown automata, it's generally fewer states than you think it is. If you want to start, you can think algorithmically. Imagine writing an algorithm for this. And because you have non-determinism in your allowance, allow yourself to be able to explore multiple branches of an if statement at the same time. You basically get to guess and go down whatever path is correct, because you get to do both paths of that at the same time. You can do the if and the else in parallel. So algorithmically, remember that we're verifying it. So I give you a string and I tell you where the midpoint is. So that means that you want to push all of the characters from W onto the stack. Then you know you're at the midpoint, so you can pop all of the characters as we read that same string in reverse. The issue that we talked about is, where is the midpoint? And I would argue that, again, this doesn't matter. Non-determinism handles it for us. Every possible character is a potential middle point of the character. If this is the middle point of the character, or sorry, the string, then start popping off those characters. If it's not what we expect, then that particular branch is going to fail. But simultaneously, we're working on every other option. While you work on that, I'm gonna try to draw out a tree for maybe visualizing this algorithmically. Because visualizing a non-deterministic algorithm is kind of challenging. So here's my hint. Here's how I'm visualizing this problem in terms of a graph. Instead of having to search this graph deterministically, where at this node, we make a choice about whether we start and say, all right, W is of length 1. Now let's check if there's a WR of length 1. I'm going to argue that we can do this at the same time. Instead of choosing here or here, we're just going to go both places. If we go both places, if this WR isn't the character that we expect, or we're not at the end of the string, then this path just rejects. As we read this character, we can decide at the same time, if we were here, is this WR? So let's again go with that case of something like A, B, B, A, B, B, A. Here is the A, and then this is the second character and second character, B, B. So is this same character in reverse? No. So AB is not a valid WWR. So this path gets rejected at the same point that we're going to start considering is AB, is the midpoint potentially here. If that's the case, then the next character that we read is a B. That's going to be this character here, but also this character here. As we read this character here, that's going to be this character here, this character here, and this character here. Now we've read enough to be able to say, is AB, BA a legal WWR? It is. This is the same as that. So if we're drawing out our NPDA correctly, then by the time we've read this, we should be able to determine, are we in a final state, or be able to teleport to a final state, or do something that says this is done. However, it's legal, but we're not at the end of the string. So we should see the bottom of stack character at this point, but when we teleport to that final state, we still have more string to read. And for that same reason that we just saw, we're going to reject. So we didn't finish reading the string. There's still more to do. So that's why this path gets rejected. And this, of course, continues out for 8 characters as we continue to do this. So the next thing would be the A here. This becomes this A here, this A here, this A here. Nothing has finished yet. So we read the next character, which is a B. So this is going to be a B. This is going to be a B, B, B. And now we've finished this potential inclusion of 3 characters, having read that. So now we can say is ABB reversed AAB. It is not, so we reject. So this is that non-deterministic view of the universe. We're considering a bunch of ifs at the same time. As we move character by character, we just make a bunch of moves at the same time. Checking, is this the end of a midpoint somewhere? So you could do this deterministically, but we're going to be simulating this with a single move all at the same time. Single move all at the same time, are we in a place that accepts? Single move all the time, are we in a place that accepts? Continuing to do that for each character. More and more and more branches of something. Does that make sense? Does that help kind of tie this back to the concept of non-determinism? Because if we were writing an algorithm for this, we'd have to say, check this, then write this here. Check this, then do this, then do this, then this, then this, then check this, then do this, then do this, then do this. Non-determinism, all of that is a single move. Think of all of that happening at the same time. Think of it as different threads that are all working independently. So maybe parallelism is another good analogy for non-determinism, except that you don't need the additional compute power of parallelism. All right, hopefully that helps. I don't know if that helped or made it more complicated, but that's how I like to visualize the problem. And let's take this idea and now turn this into an NPDA.
Then it's non-deterministic. Can you have multiple transitions like an
Yeah,
NFA?
yeah,
Okay.
yeah, you have full power, and with non-determinism, you go down both at the same time. And if one of them leads to success, then you accept. It doesn't matter if, and eventually maybe you have 80 paths. If one of those paths leads to acceptance, then you accept. It says, there is a way that I could parse this. And deterministically, you'd have to check one, then the other, then the other, then the other, but non-deterministically, we do them all at the same time. And can determine in this number of steps, if one of those paths led to success. The question that I have for people who are thinking or writing, what do the different states of the NPDA represent? I would argue that this can be a three-stater. Depending on how you're thinking about this, 3 states in the solution. What do each of those states represent? Any ideas or guesses? I would argue that the first state should be all of the possibilities for pushing a component of W onto the stack. Eventually, you're going to make a transition that says, I am done pushing W, and it is time now to pop off WR. That second state should be all of the operations that involve popping WR off the stack. The third state is going to be a final state that we transition to if we find the bottom of stack character without reading any input, just like before. And then if we happen to be at the end of the string, then we can accept. So it is very similar to the last one, just with one extra state that is the transition from W to WR.
These, we don't have to rule out anything that's not in the language, it just needs to accept.
Right. Yeah, if you were to read some character that doesn't have a transition for it, you would automatically reject. But this tells you here, W is in this language, AB plus, which tells you that the only characters in the language that it accepts are A and B.
So can you just have the first state just, every time you have an A, you put a 0, every time you have a B and you put a 1, you just keep doing that over and over again.
Yep.
But then
Let's draw that part out. I think that's a great place to start. So let's do that. We're gonna, in our arrow, include our pushing of the bottom of stacked character on to the stack. So we're going to say that with no character read, we're going to pop nothing and we're gonna push the bottom of stack character. Getting us to Q0. Now we're in Q0, so we have some transitions that can be done as we read W. Since it's non-deterministic, we don't need to have any computation about where the middle is. At any point, we can just start teleporting to doing that. This represents here. We're going to teleport to reading W sub R after we read the first character, at the same time that we consider W having 2 characters. At the same time that we're thinking about W having 3 characters, we start parsing WR if W was 2 characters. So each time there is a branch between considering a new character of W and starting a new path of W sub R. So we're gonna state these as rules when we read an A. So we're going to say the character we read is an A. If the bottom of stack character is a Z, then we want to push on, let's say 0Z. The 0 representing the A. We need another transition that says if we read a B and the bottom of stack character is there, we're going to push 1Z. And I'm already drawing this too small. We need a third transition because now we need to consider what happens if a 0 or a 1 is on the stack. So we read an A. There's a 0 already on the stack, we want to push another 0. We need another transition, or if we read an A and there's a 1 on the stack, we want to push a 0 on top of that 1. Now we need 2 transitions for reading Bs. Another transition for we read a B, there's a 0 on the stack, we want to push a 1 on top of that 0. And another transition that says we read a B, there's a 1 on top of the stack, we want to push another 1 on top of that.
So then after that, we transition to the next one, but with A, lambda, lambda. So that way, if you read an A, don't do anything because you want to give it the option, right?
I'm actually going to make this a complete lambda transition, kind of like the NFA's lambda transition that says at any point we can just teleport and start popping characters off the stack. You could make this 2 transitions that force you to read a character.
Could you make it just like 1 lambda or do you want like 3?
So let's actually think about, let's think about it. So there actually is a problem with the straight lambda idea. Let's actually talk about why that is. If I wanted to do that, we would say we read nothing in the input and we want to pop nothing and push nothing. So that's a full lambda transition. Pop nothing, push nothing. This just says we can teleport regardless of the stack contents and regardless of where we are in the input. If we do this, what's the flaw? Can anyone see what the issue is going to be? Yeah.
Except the empty string.
Yes. This says that we need at least 1 A and B. So that tells us if we can teleport here and then teleport to a final state, if the input string were the empty string, we could get there and be at the end of the. I guess technically we would want to see a Z and push a Z, wouldn't we? Not lambda. We would want to see a Z, push a Z. My bad. That's the correct notation for that.
If you want to just have nothing.
Yeah, because we would have to see the bottom of stack character.
I have one more full state that then goes to a final.
Yeah, but we definitely still want that, but I would argue even if we do this, it would accept, with that extra logic, it would accept the empty string. So now we need to make this transition actually have components to it. So we're gonna do that. I'm actually gonna write 1 on top and 1 on bottom to avoid drawing 2 arrows.
So would it be A, so when it input an A, then it would pop to 0, and then just push nothing, and then it'd
We
be.
only wanna make this, I guess, yeah, no, we need 4 transitions, don't we? We need to worry about the case of there being an A, 0, 0, saying we're gonna do a no op to the stack. read the A. But is this still part of the push?
Do we need to read the character if we're requiring there to be a 0 or 1 on the stack already?
Because we can do this directly from here. So we would say basically, what is the last A and B that we read? So we would have two options. If we stay here, we're moving in this direction. And if we move here, we're reading the first character of the next direction.
Yes, that would work, but could we do it without reading the character? By
You would have to force there to be some transition here, or force there to be some transition here. Or force there to be some character that's being read to get to the final state.
I didn't miss the start of this, so I.
Yeah, you're good.
Understand, but the second part of the notation is popping from the stack, right?
Yeah,
If we have to pop a 0 or a 1, we don't accept Z, then. that
yeah,
means
okay, yeah, I see where you're
we have
coming
to
from.
provide something.
Yeah, if we force this to be a 0 or a 1, we can't make this transition right away. So we have to have done one of these transitions first. That is right, yeah, so we do only need 2 of these. So B, 1, 1, if we do that, then, yeah, then we had to have done at least one of these before. That makes sense.
Could you replace, so the first state is building up the whole string, and the second state is just getting rid of it by just reversing it. Could we just start that process on that transition? By just putting like a lambda instead of a 0? Or the
I
1?
think we still need 4 of these, A 0, A 1. Because we still, when we read that A, it still needs to be part of either W or W. We can't.
Yes, but do we need to read the A? If we just put.
Oh,
lambdas
yeah,
first,
okay. I see what you're saying. Yeah, lambda with a 0 or a 1. That is the simpler way to do this. You're very right. So make the lambda transition. Don't read anything. Force there to be a 0 on the stack.
Mhm.
Keep that 0 there. Read nothing on a 1, force there to be a 1. Yeah. You're right. You are right. This is simpler. This is what happens when I don't refer to the solution first. We're almost out of time, so we should finish this up. Yeah,
So then the next state would just be 2 things. It would just be Q1, and then it would be just, so if it inputs an A, it's gonna pop a 0, other than just lambda, other than push nothing. Then if it's a B, it would pop a 1 and then push nothing. Because you're building a string and you want to just get rid of the string. with
Right.
something to say.
right. Yeah, so you want to say if there is an A, then we have to have seen the character that was an A on the stack from before. We don't want to have options now for popping the thing that we don't expect. That should reject, so we don't want to have logic for that. So yes, we want to loop and say, if we read an A in WR, what has to be true about the top of the stack? Has to be a 0. Yeah, we want to map it to the reverse of what was put on the stack here. So if there's a 0, we can pop it. If there's a 1, there shouldn't be a transition for that. We should reject outright. Same thing for a B. If there's a 1 on the stack, then we're reading it in reverse order, so we can get rid of it. But if there's a 0 on the stack, it would map to something we don't expect.
I have another question.
Yeah,
I like what you did with the transition, but could you also just, because this is what I put down, I don't know if I can do this. Can you,
Yeah.
instead of the lambda 1, can you just do like a 0 lambda? And just start that process as soon as you get it? Like it doesn't make it any better or change it, but just, is that another option?
yeah, I think it would be. I can't see an issue with that off the top of my head. You start the WR process because we know WR is going to be of length at least 1. And if we allow this to be a lambda transition, then this would say, yes, this is reading the first character of that rather than kind of teleporting over and then potentially reading that. Yeah, I think you could bring that forward as long as these are the same as that. Yeah, I don't see a problem with that.
And then the last one, which is transition with lambda Z lambda into a final state.
Yeah, we need a transition to a final state that says we are going to move to Q2, which is final. And the transition for this is we need an empty stack. So we're not gonna read a character. We need to see that bottom of stack character. And now we need to make the decision of, do we expect this to be empty? Or do we expect this to have the bottom of stack character when we're there? So again, we get this option of, are we gonna include a Z here or a lambda here? Based on whatever we decide. The acceptance criteria for this is. So that would do it. And again, this is kind of gross to visualize. I would argue that it might even be better to write these out as just a sequence of kind of like an assembly program where you have a title and then you have a bunch of instructions for that comment. Basically, that's how readable assembly is. You write a comment and you write all of the instructions that are relevant to that comment. And then another comment, all of the instructions that are relevant to that comment. You would have something like Q0, all of the transitions that are associated with the comment of pushing to W. Another one that is all the rules associated with transitioning from W to WR. Another one that is the rules associated with recognizing WR. And another one that recognizes the end of string and acceptance. And if you kind of broke this down into category, 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 then you could write this as a list of transitions and categorize them. As these get more and more complex, that becomes more and more ideal. Because looking at this, if we hadn't built this idea from this idea, how readable is this? How long would it take you to figure out, if I just gave you this, what does this machine do? And this isn't even that complicated of a language. So it gets worse and worse as these languages get more and more complicated. Anyway, we're far from overtime. But that's it for today. Reminders from yesterday, we have an exam a week from today. There is a study guide live on Canvas. So you can go take a look at that. We'll dedicate next Thursday's class to questions about that study guide. I revealed the homework yesterday. It isn't due for 2 weeks. Worry about the exam next week. And if you'd like to get started on the homework, but I'm trying to not make you choose between those things. For the scope of this class, focus on the exam mostly next week, focus on the homework the week after, but we've covered some of the content to be able to start on that homework. All right, have a great weekend.